Hello students, in today's video we're going to be working on the fundamental theorem of calculus. So let's go ahead and get started. So go ahead and try this warm-up problem, pause the screen and try solving it on your own. Hopefully you're coming back and just try and check your answer now. So remember, when we take the antiderivative of sine of theta, the antiderivative is going to be cosine of theta, but because, we're going to use cosine x so it's faster, but because when we took the derivative of cosine, it wasn't equal to negative sign, we need to throw a negative back in here. Now we're integrating this from pi to 0. So what's going to happen is we're going to substitute pi in here minus cosine of 0. And we know that cosine of pi is equal to negative 1. And then the two negatives become a positive here. And cosine of 0 is equal to 1. Therefore, we're going to get this is equal to 2. So hopefully your answer checks out. Let's go on and talk about the fundamental theorem of calculus. Now, the fundamental theorem of calculus states that if a continuous function on the closed interval AB, or is continuous on the closed interval AB, then the function has an integral from a to x of f of t dt, which is equal to the antiderivative big F of x. So bottom line, it's stating that if a function f is continuous on AB and has a derivative at every point in AB, then it's a derivative of some other function. So notice if you take a look here, we're taking that f of t dt and somehow it's changing to f of x. So we'll talk about that a little bit more. So every continuous function is the derivative of some other function. Every continuous function has an antiderivative. And the process of integration and differentiation over inverse are inverses of one another. So remember, this is what we're saying. Derivatives and integrals are opposites of each other. So let's try some practice problems. So here we're going to find the derivative of y equal to the integral from 3 to x squared for t squared of sine t dt. So remember, this is where the fundamental theorem of calculus comes into play. All we're doing here is we're substituting these values in. Now it says we're finding derivative here. So really what's happening is we're taking t squared of sine t dt and we're substituting those values in. So we know that t is we're going to replace with x squared, and that was always squared, so it's x squared squared, sine of x squared. This is where we multiply by dt. So the derivative of x squared is 2x minus 3 squared sine of 3 times the derivative of 3, which is 0. So therefore, we're really going to just be left with x to the 4th sine of x squared times 2x, because the rest of this, because you're multiplying a 0, becomes 0. And finally, you have 2x to the 5th sine of x squared. So hopefully that worked out. Remember, all we did, we substituted the lower limit and the upper limit, and we found the derivatives of each, and that's how we got our answer. So let's try another one. So find the derivative y equals the integral from negative 1 to 3x for the quantity t squared minus 4 to the 5th power. So let's start off with the basics. We have t squared minus 4 to the 5th power dt. And we're replacing 3x squared minus 4 to the 5th power. Derivative of 3x is just 3. Minus, remember, because the bottom limit or the lower limit is a constant, it's eventually going to be 0. So here we're left with 3 times 9x squared minus 4 to the 5th power, and we are done. So hopefully you're finding this to not be too difficult. If not, make sure to ask me in class. But let's try yet another one. Notice here this one's a little bit different because it has x on the lower limit and on the upper limit. So this shouldn't be too bad. So let's take a look now. We have ln of t plus 5 dt, and now we're replacing, right? So we are going ln of 5x plus 5 dt, which is just 5, minus ln of 2x plus 5 times 2. And that would be your final answer. There's not much we could do to it other than just to leave it there. So let's move on. So find the derivative of 3 divided by e to the t plus 1 from x to x squared. So this is going to be a lot of the same. So 3 divided by e to the t plus 1. And what we're going to do here is we're going to replace that. So we draw a fraction bar. That's not a negative. Okay. And now we're replacing. So we're going to go ahead and put in 3 divided by e to the x squared plus 1 times dt, so that'll be times 2x. This is a fraction, minus 3 divided by e to the x plus 1 and then we're going to multiply that by derivative of x, which is just 1, and this is your final answer. So let's try one more. This one's a little bit more tricky. Notice here that the upper limit and the lower limits have been switched. So what we're going to do here is we're going to integrate now from 5x squared from x to 5x squared. And because I switched the limits, we're going to put a negative in front. And now we have 2t minus 3 dt. Now we're going to go ahead and replace again. So we have a negative in front, so we're going to keep that in mind. A negative is in front. Notice it's in blue. We're going to replace now. So we have 2 times 5x squared minus 3 times dt, so that's 10x, minus 2 times x minus 3 times 1. This turns out to be 10x squared minus 3 times 10x minus 2x minus 3. Keep in mind there was a negative in front of the whole thing from the beginning. So we're going to put that negative back over there. And now we're going to be left with negative 10x. Notice I pulled the 10x to the front, put the negative in front, times 10x squared minus 3 plus, because the negative times the negative is positive, 2x minus 3. And that's your final answer. You can clean it up if you want, but remember, we don't have to. So let's look at the second part of the fundamental theorem of calculus. In the second part, it states that if f is continuous at every point on the closed interval AB, and f, big F, capital F, is an antiderivative of f on the closed interval AB, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. This formula is also called the integral evaluation theorem. It basically means if we take that f of x, we integrate it, and we substitute the upper limit, b, into the antiderivative, and we subtract the lower limit of the antiderivative from the upper, you'll have your answer. You're basically just evaluating that. So let's look at some examples. So evaluate x squared minus 2x dx without a calculator. So first thing we're going to do here is just to make things clear, we're going to write down what we have. So x squared minus 2x. We're now going to find the antiderivative, which is going to be x to the third power divided by 3 minus x squared. So that's our antiderivative for the function. And now remember, we're going to integrate that from 3 to 1. So what that means here is that we're substituting. We're going to end up having 3 to the third power divided by 3 minus 3 to the second power. Notice I just substituted the 3 into each x, minus, because now we have to subtract the lower limit, minus 1 to the third power divided by 3 minus 1 to the second power. This is going to end up giving us 27 divided by 3, which is 9, minus 9, because 3 squared is 9, minus 1/3 minus 1. That's going to end up giving us 0 minus negative 2/3, which is just equal to positive 2/3, and that would be your answer. So let's look at another type of application for the fundamental theorem. This is finding the area between two curves. It says the signed area between two curves f and g on an interval between a to b is given by the integral from a to b of f of x minus g of x dx. Now, to find the total area, we find any points of intersection of f and g, then integrate each region separately and add their absolute values. So this part's really important. We have to include the absolute values in here because what's happening is sometimes you're going to have a negative area, which we all know is impossible. But that happens in math because sometimes your graph goes below the x-axis. So to accommodate for that and still give a positive area, we're throwing it in the absolute value. So let's look at a couple examples now. So it says find the total area of the regions between y equals x squared minus 2 and the line y equals x from 0 to 3. So let's take a look at that graph. Here we have, notice it says we integrate from the intersection. So here we have an intersection at 0, 2. Now what we're trying to do here is we're going from 0, which is right here, to 3, which is right here. So what we're trying to do is we're trying to find that area now. So essentially we're trying to find the area from here to here. Notice I'm starting at 3 and I'm going backwards just to make sure you all see it. And so now what we're doing here is we're integrating. We're integrating twice because there's a point of intersection. We're going from 0 to 2 because that's where it intersected at 2. And then 2 to 3 because we want to stop at 3. But there was an intersection in between. We're going to add up those two areas and they're going to be in absolute values. So what we're going to put inside the absolute values is x squared minus 2 minus x. So notice this was the first function and the minus x was the second. So what we're going to do now is we're going to do the same thing here. Okay. So now what we're going to do is we are going to evaluate this by taking the antiderivative of each one. So this first one's going to become x to the third power divided by 3 minus 2x minus x squared divided by 2. And the same thing would happen on the right side. And then remember, we're integrating this from 0 to 2. And so what's going to happen there is we are going to get absolute value of negative 10/3 on the left side. And we add the right, we are going to get 11/6. And when we add those two things up, that total is going to give us 31/6 as our area between the curves. So that basically means, and I'm going to do this in red, this area was 10/3, and this area was 11/6, and when we add them up, we got a total area of 31 divided by 6. So let's try another problem. So now we want to do one from 4 minus x squared and the line y equals 3 from 0 to 3. So I'm going to get rid of these graphs and put up the two new ones. Notice here, we're still going from 0 to 3. And notice there's an intersection point right here at 1, 3. So again, keep in mind, we're trying to find the area from 0 to 3. So that basically means here, because notice it says area between the curves. And this is between the curves. And so is this one from here to here. Notice that there's another intersection point right here. 2, 0. And remember, we have to go from there to 3 as well. So it's these three different regions that you see here that we're going to find the areas of. So we're going to integrate 3 times because there's 3 different regions. So we're going from 0 to 1, because that's where 1 is right here. And then we're going from 1 to 2. It's another little region. And then we're going from 2 to 3. And then we're taking the absolute value of each one. We're adding them up. And our function here is going to be what we started with, that x squared, or 4 minus x squared. We'll pull it back up. 4 minus x squared and then minus 3. So it's the first function, so let's type that in. 4 minus x squared minus 3. So that's the function we're integrating with respect to. So we're going to do it once, twice, and thrice. So when we do the integration here, we're going to end up with 2/3. That's odd. Okay, 2/3 plus the second one's going to be 4/3, and the last one's going to be 16/3, and our final answer is going to be equal to 22/3. So when we integrate these 3 sections, you get 22/3. Now I've shown you how to do this on your calculator, so that's another option for you, but you really want to make sure you're doing this by hand and checking with a calculator, because you're not always going to have a calculator there with you. So I've shown you how to do this on the calculator, but just in case you forgot, if we need to find the area numerically, you're going to punch this into your calculator. So this is where you press the math button on your left hand side and scroll down to where it says fn int, like it says here, and you're going to type in the absolute value of the function, comma x, comma ab if you're using 83s. 84s will look exactly like you see it or how you wrote it down. To find the area between the two graphs, notice we have the absolute value and f of x minus g of x are in the same parentheses. Otherwise, it's not going to be correct. So that's all for now. I'll see you guys next time.